In this video, we will learn how to find intervals of concavity and points of inflection algebraically. I have a separate video on how to do this graphically, just by looking at a graph. And if you haven't watched that video, I'd encourage you to watch that one before you watch this one. Then we will practice some free response and multiple choice questions pertaining to this topic. Let's begin by reviewing concavity and points of inflection. A function is considered to be concave up when f prime, the first derivative, is increasing, or when f double prime, the second derivative, is greater than 0. A function f is considered to be concave down when f prime of x is decreasing or when f double prime of x is less than 0. Points of inflection are points where f changes from concave up to concave down or vice versa. So they are points where the concavity changes. If you only have information about f prime, you can tell when there's a point of inflection because f prime will change from increasing to decreasing or vice versa at the point of inflection. F double prime changes from positive to negative or vice versa at points of inflection. So how can we find points of inflection algebraically? This is the new topic for this video. Well, we need to look for points where the second derivative is equal to 0 or undefined. These are potential points of inflection. However, they are not guaranteed points of inflection. Let's take a look at y. If we have the function y equals x to the fourth and we're trying to find the points of inflection, we first need to find the second derivative. So y prime would be equal to 4x cubed, y double prime would be equal to 12x squared. And we can see that when we plug in 0 for x, when x is equal to 0, y double prime is equal to 0. The second derivative is 0. So this is a potential point of inflection. However, if we look over here at the graph of y, x equals 0 is not actually a point of inflection because y does not change concavity at x equals 0. Y is concave down this entire time. It doesn't change from concave up to concave down or vice versa. Therefore, x equals 0 is not a point of inflection. So the conclusion here is just because the second derivative is 0 does not guarantee that there is a point of inflection. It just means that there might be one there. The steps to find points of inflection and concavity are as follows. The first step is to identify the domain of the original function if possible. This step is optional, but I find it helpful because you know that a point of inflection cannot exist outside the domain of a function. So if you get a point of inflection that's occurring somewhere where the domain does not exist, then you know that that can't actually be a point of inflection. The second step is to find the second derivative. Then the third step is to find the values of x that will make the second derivative equal to 0 or undefined. These are potential points of inflection. Then you make a sign chart with the points of inflection and the domain issues. You test the sign of the second derivative on each interval, and then you can write a conclusive statement. Here are some examples of proper justifications. These are the same justifications that we used when we were looking at a graph, but this time we're going to apply them to equations. If you're trying to justify why f has a point of inflection somewhere, you can say f has a point of inflection at x equals blank because f double prime of x changes signs at x equals blank. That's probably the one that we'll be using most often because we go up here and find the second derivative, so we will have information about the second derivative changing signs. However, you could also say that f has a point of inflection at x equals blank because f prime of x changes from increasing to decreasing or vice versa at x equals blank. If you're talking about concavity, you could say f is concave up on the open interval from a to b, not the closed interval from a to b, because f double prime of x is greater than 0 on that interval. This justification is the one that we will be using most often. However, if you only had information about the first derivative, you could also say f is concave up on the open interval from a to b because f prime of x is increasing on that interval. Find the intervals on which f of x equals 2x to the fifth plus 1/2 x to the fourth minus 3x is concave up and down and identify the points of inflection. Justify. The first step is to find the domain of the original function. In this case, the domain of f of x is going to be all real numbers because this is a polynomial. The second step is to find the second derivative. So first I will find f prime of x. F prime of x is going to be 10x to the fourth plus 2x cubed minus 3. Then I will find f double prime of x. F double prime of x will be 40x cubed plus 6x squared. The third step is to find the values of x that will make the second derivative equal to 0 or undefined. And these are the potential points of inflection. There are no values of x that I can plug in that will make f double prime of x undefined, but I can set f double prime of x equal to 0 and then solve. Now I can factor and solve. These are my potential points of inflection, x equals 0 and x equals negative 3/20. So now I will make my sign chart with my points of inflection and my domain issues. I don't have any issues with the domain here because it's all real numbers, but I will put my potential points of inflection on the sign chart. And I'm going to label my sign chart as f double prime of x. Now I need to test what f double prime of x is in each of these intervals. So for this interval, I will find f double prime of -1 and see whether it's positive or negative. This is -34, which is a negative number. Now to test in this interval, I will test f double prime of -1/10. This is going to turn out to be a positive number. It's going to be 20 over 1,000 or 2 over 100, which is positive. And then I will test f double prime of 1. This is 46, a positive number. So now I just need to write my conclusive statement. And I have my information here about f double prime. First, I'm going to explain where f is concave up. F will be concave up on the open interval from -3/20 to 0 and the open interval from 0 to infinity because f double prime of x is greater than 0 on those intervals. Notice that I did not include 0 in here because f double prime of x is actually equal to 0 at 0. F is concave down on the open interval from -infinity to -3/20 because f double prime is less than 0 on that interval. F has a point of inflection at x equals -3/20 because f double prime of x changes signs at x equals -3/20. And note that even though we had identified 0 as a potential point of inflection, that one is not an actual point of inflection because f double prime is positive on both sides of 0. This is my full justification. Find the intervals on which f of x equals 3x minus 1 over x plus 7 is concave up and down and identify the points of inflection. Justify. First step is to find my domain of f. In this case, I can plug in anything I want for x except -7 because that would make f of x undefined. So the domain will be all real numbers except for -7. The next step is to find f double prime of x. First, I'm going to use the quotient rule here because I see a quotient to find f prime. So I have f prime of x equals 22 over x plus 7 squared. And then to find f double prime of x, I will use the quotient rule again. Here's my second derivative, f double prime of x. Now I need to find my potential points of inflection by determining which values of x will make the second derivative equal to 0 or undefined. If I plug in x equals -7, that will make the first derivative undefined because the denominator will be equal to 7. So x equals -7 is one of my potential points of inflection. However, we've already established that x equals -7 is not within the domain. So I'm going to cross that one out and just make a note that says not within domain. So are there any values of x that will make the numerator equal to 0? Yes. What I'm going to do up here is set the numerator equal to 0 and then solve that to see if there are any other potential points of inflection. Unfortunately, what I'm getting up here is also x equals -7, which we have already established that's not in the domain. So I don't have any points of inflection here. When I make my sign chart, I'm not going to have any points of inflection to write on it, but I do also include the domain issues on my sign chart. So my sign chart is going to look like this. Now I'm going to plug in values for f double prime. So first I'm going to find f double prime of -8 and see what I get there. This is 44, a positive number. Then I will find f double prime of 0 to test in this range. This is -308 over 7 to the 4th, which I know is going to be negative. So now I have to be really careful when I'm doing my explanation because this really looks like it would be a point of inflection because the second derivative is changing from positive to negative. However, x equals -7 is not within my domain, so that is not a point of inflection. F is concave up on the open interval from -infinity to -7 because f double prime is greater than 0 on that interval. F is concave down on the open interval from -7 to infinity because f double prime of x is less than 0 on that interval. F does not have any points of inflection because there are no points within the domain of x for which f double prime of x changes signs. This is my full justification. Identify the points of inflection of h of x equals the cube root of 5x plus 5 squared, if there are any. Justify your answer. First thing to do is to identify the domain of h. In this case, I can plug in any value of x that I want here because I'm taking the cube root, so it can be negative under this radical. So the domain of h will stretch from -infinity to infinity. Next step is to find the second derivative. I'm first going to rewrite h of x as 5x plus 5 to the power of 2/3 to make it easier to use the power rule. Then I will find h prime of x. Then I will find h double prime of x. There's my second derivative. So here I'm just looking for points of inflection. So now I'm looking for values of x that I can plug in that will make the second derivative equal to 0 or undefined. There are no values of x that I can plug in that will make h double prime of x equal to 0, but I can set the denominator equal to 0 to see if there are any values that will make h double prime of x undefined. When I solve that, I get that there is a potential point of inflection at x equals -1, because if I plug in -1 for x, then h double prime of x will be undefined. However, remember, just because you're getting it as a potential point of inflection doesn't mean that it actually is one. The criteria that a potential point of inflection must meet to be considered a real point of inflection is that f double prime, or h double prime in this case, must be changing signs at that point. So what I'm going to do is I'm going to make my sign chart. And I'm going to find h double prime of -2. Now, I don't want to evaluate this, but I don't actually have to. All I need to determine is it positive or is it negative? So I know that I'm going to have -50 over a positive number, because -5 to the 4th power, that's 625. If I take the cube root of 625 times 9 times the cube root of 625, that denominator is going to be a positive number. So I have negative over a positive, which is negative. So it's negative in that interval. And then I will test h double prime of 0. Again, I know that 9 times the cube root of 5 to the 4th will be positive. So I have a negative over a positive, which is a negative. Since h double prime of x is not changing signs at x equals -1, this means that x equals -1 is not, in fact, a point of inflection. H does not have any points of inflection because there are no values of x at which h double prime of x changes signs. On the closed interval from 0 to 2 pi, the function f of x equals 6 times the cosine of 1/3 x plus 1 has point or points of inflection at x equals, and then we have these options down here. So this is a multiple choice. First step is to identify the domain of the function. They gave us the domain. It's from 0 to 2 pi. Now we need to find f double prime of x. F double prime of x is equal to -2/3 times the cosine of 1/3 x. Now I need to determine which values of x are going to make f double prime of x equal to 0 or undefined. There are no values of x that I can plug in that will make f double prime of x undefined, but I can set f double prime of x equal to 0 and then solve. So now I need to ask myself, what values could I plug in for this? We'll call this theta, that would make the cosine of theta equal to 0. So I know that the cosine of pi over 2 is equal to 0, so we can say theta is equal to pi over 2. I also know that the cosine of 3 pi over 2 is 0. So theta could also be 3 pi over 2. And then I will set theta equal to what's inside here. So I will say 1/3 x could be equal to pi over 2. This means that x could be equal to 3 pi over 2. And then I will set 1/3 x equal to 3 pi over 2. This means that x could be equal to 9 pi over 2. However, 9 pi over 2 is not within the domain, so I'm just going to make a note there that says not within domain. 3 pi over 2 is within my domain. But first, I need to check that this is an actual point of inflection. I need to make sure that f double prime of x is actually changing signs there, and it's not just a potential point of inflection. So I will make my sign chart, and I'm going to test f double prime of pi over 2. This is negative rad 3 over 3, so a negative number. And I forgot to label my sign chart. I forgot to say that this is f double prime. And then I will find f double prime of 7 pi over 4. Now, I'm running into a bit of an issue here because cosine of 7 pi over 12, that's not a value that I have memorized. What I'm going to do, though, because I really just need to determine is the cosine of 7 pi over 12 positive or negative, what I'm going to do is I'm going to go sketch out a cosine curve. So 7/12 is a little bit more than 1/2. It's a little bit more than 6/12. So this means that cosine of 7 pi over 12 is going to be right around here on my cosine curve. It's going to be just a little bit to the right of this pi over 2. This means that the cosine of 7 pi over 12 is negative. So I have -2/3 times a negative value. This is a positive value, and that's all that I need to know. Now I have verified that this is an actual point of inflection. The point of inflection is occurring at x equals 3 pi over 2. Let the first derivative of the function f be defined by f prime of x equals negative e to the power of 1/2 x plus cosine x on the open interval from -1 to 3. On which interval or intervals is f concave up? This is a bit of a different problem because instead of giving us the regular function f, they already gave us the first derivative. They did one of the first steps for us. Very first step is to identify the domain. And they gave us the domain. They said the domain is from -1 to 3. However, this is the domain of f prime of x. So I'm just going to make a note, domain of f prime is the open interval from -1 to 3. Now I will find f double prime. So I just have to take the derivative once though, because they already found f prime of x for me. And I will have to use the chain rule a lot here. So first it will just be negative e to the power of 1/2 x plus cosine x. That just stays the same because e to the x is its own derivative, multiplied by the derivative of the inside function, which is 1/2 minus the sine of x. Now I need to determine if there are any values of x that I can plug in that will make f double prime of x undefined or equal to 0. There are no values of x that I can plug in that will make f double prime of x undefined, but I can set f double prime of x equal to 0. And then 0 will be equal to this chunk, and then I can evaluate those separately. So we run into a bit of a problem here because to cancel out the e, what we have to do is apply the natural log to both sides. So we would say natural log of 0 is equal to natural log of e, and then those natural logs and e would cancel, but we cannot take the natural log of 0. So I'm just going to make a note here and say can't take natural log of 0. And that's where that one stops. So then I will say 1/2 minus the sine of x is equal to 0. This means that 1/2 would need to equal the sine of x. And what values can we plug in for x there? Well, on the interval from -1 to 3, the values of x that we can plug in are pi over 6 and 5 pi over 6, because the sine of pi over 6 is 1/2 and the sine of 5 pi over 6 is 1/2. This means that these are my potential points of inflection. Now I'm going to make a sign chart. First, I'm going to find f double prime of 0 to test the sign in this interval. This is negative e times 1/2, or negative e over 2, which is a negative value. So negative goes right there. Then I will test f double prime of pi over 2. This is negative e to the power of pi over 4, which is this entire thing is a negative number, times negative 1/2. So multiplying those together makes a positive number. And then to test the second derivative in this interval, I want to plug in pi because pi is greater than 5 pi over 6, but pi is not within the boundary here because pi is greater than 3. So instead, I'm going to have to test f double prime of 11 pi over 12. Now this is posing a bit of a problem because 11 pi over 12 is not a value that we work with frequently on the unit circle, so I don't have that one memorized and I don't know what it is. So what I'm going to do is sketch out a sine curve. Now, I know that 11 pi over 12 is almost 2 pi. So 11 pi over 12 is just going to be a barely negative value there. So if I have 1/2 minus the sine of 11 pi over 12, that's still going to be a positive number. So I have a positive number times and then negative e to the power of 11 pi over 24 plus the cosine of 11 pi over 12. E to any power is positive. So if I have a negative times a positive value, that makes a negative value. So that means that I have a negative value times a positive value. So f double prime of 11 pi over 12 is going to be a negative value. So I can fill in the negative on my sign chart there. And the question is asking me on which interval or intervals is f concave up? Well, f is concave up on the open interval from pi over 6 to 5 pi over 6 because that is where f double prime of x is greater than 0.